looking at the theorem, suppose you have a continuous function with a domain A. If you have a subset of A that's connected, then f of that subset is also connected. And I'll give you an example and a non-example, then I'll run you through the proof, the idea of the proof. So in both the example and the non-example, my f is 1 over x, my domain is everything but 0, and in my example, E is going to be the interval 1, 2. So to see what happens here, right, between 1 and 2, what happens here? I want this to be blue. Blue is prettier. What's happening here? Between 1 and 2, I basically, that part here, which means that that part's f of e. Translating it over here, I get the interval from 1 to 1/2. So in other words, if my interval is 1, 2, that means f of e is going to be 1/2 comma 1, where basically 1 goes to 1 over 1 and 2 goes to 1 over 2, like so. So this is just a straightforward computation to tell you what the theorem is saying. And in particular, what this is saying is that, hey look, you have this connected part right here. It maps to a connected part. And of course the punchline is this is connected. So this theorem says that without doing this computation, this picture, we would already know that whatever f of 1, 2 is, it's going to be connected. Let's contrast that with what happens if I pick, say, -1 to 1, where I have to exclude 0 because 0 is not in the domain. Well, let's do something similar. Let's figure out what happens. -1 is going to go down to 1, and then all the way to 0, it's going to go all the way down to infinity. Similarly, from 1 to 0 means I'm going to take this part. So my f of e is composed of these two chunks, which is really, if I map them over, maps from 1 up to infinity. So that's going to be part of my interval is 1 to infinity. That's the kind of left side. And I also go from -1, or negative infinity, sorry, to -1. Now, the important thing here is that this is really not related to the theorem at all. But if I don't start with a connected set, I'm not guaranteed that it's connected. It might be connected, right? Because this is not related to the theorem, because the theorem only says two things. It says if you start with something connected, you're guaranteed to end up with f of e being connected, like over here. This is useful for the theorem. But also the contrapositive is true. If f of e is not connected, then e was not connected, which is not the situation. Okay, now let me run through a sketch of the proof. The proof basically says, okay, we need to prove that f of e is not is connected. So let me draw. Here's the picture of f of e right here. I'm drawing in 2 dimensions because that would get the basic idea down maybe a little bit better. And let's suppose, right, I might encourage you to look at the definition of separated sets. But let's suppose for a second that I can draw 2 circles, A, and how about B will be in purple. That'll be part B, where what I know is that A intersect B is the empty set. These are completely disjoint, and also they're non-empty. Look, B contains some stuff, A contains some stuff. Well, I'm going to prove that f of e is connected by doing the following. I need to find some sort of a sequence that starts in 1, maybe y1, y2, and converges to some sort of a y in B. So that's going to be my goal. That's going to be how I tell if this is connected. So that's the theorem that we saw already. So I'm going to start off with 2 disjoint sets that are both non-empty, such that f of e, I should write that down, f of e equals the union of these. That's an important thing to point out. So A is just this bottom part. I drew the circle, the red circle a little bit bigger and the purple circle a little bit bigger, but that's the basic idea. They're disjoint, and I'm going to show that there's a sequence that is completely contained in one of them, but has a limit in the other, and that'll be enough to show that they're connected. In the next screencast, I'll show you exactly how that is done.